Hello, friends. Today we would be doing one of the most popular neural network models by the name Feedforward Backpropogation neural network. I am Pankaj Agrawal from IMS Engineering College. So let us first try to understand what exactly this backpropagation, feedforward backpropagation neural network is all about. See, as the name tells you, feedforward. So it comes under the category of feedforward networks. And there's another term called backpropagation. So here we are talking about backpropagation of errors, right? So feedforward means all the errors would be and all the calculations would be done in a feedforward manner. But once we would be calculating the error between the calculated outputs and what is expected, then we would backpropagate those errors to all the weights in the back format manner, where we would be backpropagating those errors, and we would be updating the weights between the output and the hidden first, and then between the hidden to the input layer. And if there are more than one hidden layers, then this process would be same as it is. So this backpropagation algorithm is in fact one of the most fundamental and the most basic neural network, and it is also the fundamental block in if we want to learn about the deep neural networks, then backpropagation is one of the most fundamental networks. This backpropagation network was in fact introduced in 1960s, and in fact almost after 30 years it took for its whether when the scientists started believing that this backpropagation can be so useful, and it was actually popularized by Rumal Hurt and then Williams in his paper titled "Learning Representations by Backpropagation Errors." So, backpropagation is in fact one of the most popular neural networks learning models. It is abbreviated as backward propagation of errors, and it is a common method for training the neural networks, which is also used in conjunction with some other optimization methods like gradient descent. So this calculation of errors and this minimization of error is in fact based on the concept of gradient descent method, which we would be covering later on. Now, this algorithm is being effectively used in training part. So it is basically a supervised learning method where we would be having training samples, and we would be having the labeled outputs. And once that training is completed, then we can apply the trained model to classify the new untrained samples. So this algorithm is actually uses something called chain rule, which we would be covering when we would be doing the example. Now, the backpropagation actually can be studied in different phases. And the first phase of the backpropagation is called the feed-forward phase, right? In the feed-forward phase, we would be giving the input to the input layers. We would be calculating the net inputs to each and every input layers. Mind you, backpropagation neural network is a multi-layer perceptron model, right? We have at least one hidden layer. So we would be calculating the hidden inputs, their activation inputs, the activation outputs. Then we would be calculating the errors at the output layers, right? So the feed-forward phase is the calculation of the output neurons. Okay, what is the output of each and every neuron in the output phase? So that is where the feed-forward phase ends. And then comes the calculation of errors. And once the feed-forward phase is done, that is, we have calculated the output from the output layers. Then comes the part which is called calculation of errors. Then we calculate the errors based on gradient descent, where we calculate the difference between your expected output and the actual output. Expected output means the target output. So once that error is calculated based on the gradient descent, then the next phase starts, which is called backpropagation of those errors. That is the backward phase. So the thing is, once the error is calculated, That means we have not been able to learn what was expected. So we would start back propagating those errors uh, back to the network, where we would be first updating the weights between your hidden and the output layer. And then if there are more than one hidden layers, then between the hidden layers, weights between the hidden layers. And then ultimately the weights between the input and the hidden layer, the first hidden layer, would also be updated. So in this way, all the weights are updated in a backward fashion, and therefore it is a backward phase, right? And then comes your updating the weights of those layers, where we already so this is done in conjunction with layer 3 only, step 3 only, where would be calculating the back propagation of errors as well as the updation of weights. And these four steps are actually done in a repeated manner till the difference between the calculated output and the target is minimized to a given range, or till the network converges. That is when there is no more error between the calculated output and the target outputs. So this is what is a general method of backpropagation learning. So we would be doing one example in order to understand all the phases of backpropagation, right? Um, the method that as I've told already, that we would be using the gradient to calculate the loss function. So gradient is nothing but basically is the first order derivative of the squared difference between your calculated output and the target output, right? So we would be, why we have taken the gradient, why we have taken the derivative, that we will study as we go along. But as of now, you understand one thing, that gradient of loss function would be used in calculation of those errors, and that error would be then back propagated, and weights would be updated in a backward fashion. Now, gradient is fed to the optimization method, is fed to the optimization method, which it turns use it to update the weights in an attempt to minimize the function. So overall concept by using this gradient function would be to minimize the error between the calculated output and the target output. The backpropagation also requires something known as the desired output for each input value, as I've just told, in order to calculate the loss function. So since this is a supervised algorithm, so for each and every input sample that we would be given to the network, we need a corresponding target value, or corresponding label, and so that we can calculate the errors. So it is therefore considered to be what? Supervised learning method. Backpropagation requires the activation function also, definitely, as like other neural networks. So the most popular activation function for backpropagation is the sigmoid function, the function which needs to be differentiable. Right? It is not only sigmoid function, we can use other functions also, but the function needs to be differentiable at least. All these questions, why this requires to be differential, why other function will not work, that we will cover later on. To begin with, let us first understand how this backpropagation, all the phases of the backpropagation works through an example. So let us understand a simple a portion of a network, suppose, where we have considered what? We have considered a neuron A, which is connected with, suppose, neuron B, and then we have this A is also connected with the neuron C, right? And the corresponding weights are also given, right? So this is not a network. This is just considered a part of a network. So we just wanted to understand first that how the errors are calculated, right? So assume that this is the A is part of the hidden layer, and suppose B and C are what? Output layers, right? So let us see that how from hidden to output layer we are able to calculate the errors, right? And how we are using those errors to then back propagate. So we would be calculating the errors at B and C respectively, and then we would be back propagating these errors so that we can update the weights. So how we backpropagate them and calculate or readjust these weights, and then how we calculate the error at A. This is how we have to do. right? So once we calculate the error at B and C, then we backpropagate the error so that the weights can be updated. And then whenever a neuron comes in the backward phase, we also calculate the errors at these hidden neurons also. And the same procedure for between the hidden and the input, right? So the network the error at neuron B can be is what is expected, what is the target value, and what we have actually calculated. So that would be the difference, right? So the first order derivative of the gradient method, when we apply it, the formula comes out to be of this fashion. How it comes, then we'll be covering later on, right? So the error at B, as of now, you just think of that we have to use this particular formula. So in order to get error, in order to calculate the error at suppose B neuron, B I'm considering here as an output neuron, right? So if I have to calculate the error at B, it would be of this form. That is, the output at B, what is the output? What is the calculated output at B, which we would be doing in the forward phase, right? And 1 minus of output B, right? So output multiplied by 1 minus of output B. This is a term which is induced because we would be using a differential function, right? If the function was not differentiable, then this term would have been absent. Right? We'll come to all these things later on. And the important part is the target B. What is the target expected output at B, and the calculated output at B. So this would be the formula we would be using for calculating the error at each of the output neurons, right? So the same formula would go for C also, with error at C, and with the same kind of symmetry, right? So the next step is the output, which I've already told, the output into 1 minus of output term is necessary in the equation because of the sigmoid function. Had there been a very simple function, no differential function, then the difference would have been simple target minus output. But that is not very useful difference, useful method for calculating the errors, right? Now, the thing is, once we have calculated those errors, we will be taking the example also, very working example also. I'm just talking right now about the formulas. Now, the thing is, now we have to calculate the weights. Weights means, now I have to see that what are the weights that we have to do what? Now we have to, since I have calculated the errors, we have seen the formulas for calculation of errors at B and C. So now we have to use this error, we have to backpropagate this error to calculate or to update the weights. That is, now I have to calculate, find some way so that I can update this weight, right? Both the weights, WAB and WAC, would be updated, right? So in that direction, this would be the formula that we would be using. That is, plus means the new weight of WAB, and WAB is the old weight, the previous weight. And this is the term that we would be using, that the error at B and output at A. Error at B, what was the error that we calculated at B, and what is the output at A? See, by doing the forward phase, I would have been calculating the output of A, definitely, right? So I'm assuming that we have already done the forward phase. During the forward phase, we would have calculated the output of A, B, we would have calculated the output of B, C, each and every neurons, whether it is a hidden neuron or whether it is the output neuron, right? So in order to update this weight, we have to add the previous weight and plus what is the error at B and multiplied by what is the output at A. So you have to remember this formula, right? In the same case, in order to update WAC, it would be WAC new would be equal to WAC old, that is the previous weight, plus the error at C into multiplied by output at A, right? I hope that is clear. The formula is pretty simple. So this is the formula that we would be using for each and every weight. But mind you, this is only between the output and the output layer and the hidden layer. When we would be coming for input and the hidden layer or the rest of the layers, then this formula would be little different. We'll see how. Now, the next is, once we are done, so next step is that we need to calculate, we have done what? We have calculated the errors at B, we have calculated the error at C, We have updated these weights also. Now I have to calculate what? I have to calculate what is the error at A. See, when because there could be layers before this network also. Before layer, there could be input layers definitely. So now, in order to update the weights prior to A, I have to calculate the error at A. I cannot use the error which I calculated at B and C in order to update the weights, each and every weight. So now I have to calculate what? The error at A, right? Mind you, this A is governed by two neurons, both B and C. So that we have to take care of. And suppose, and also we have already updated this to weights which are associated with A. So the formula that we would be using would be, so calculating the error at A implies the same method would use, right? The output at A into 1 minus of output of A, right? And what is the error at B? Error at B is what? We already calculated for error B neuron, right? And what is this WAB is not the old weight. It should have been plus. This is the updated weight, right? So W plus AB, right? And similarly, what is the error at C? This is because A is associated with both B and C. That is why we have to use this addition, right? So error at B into WAB, that is the new weight that we have updated just, and plus the error at C into WAC, again the new weight of WAC. So how it looks like, in order to update this, in order to get this out error at this neuron A, so I have to take the term output at A, right, multiplied by 1 minus of output at A. That term would always be there. And then since A is associated with B and C, so what is the error at B, right, which we have already calculated, multiplied by this updated new value, that is W plus AB, right? And plus, again, what is the error at C, and multiplied by the WAC plus, that is the new weight that we updated. So this would be the formula in order to get the error at A, because it is being linked with both B and C. Right? I hope that formula is clear now. So again, the factor output and 1 minus of output is present because of the sigmoid function that we're using. Mind you, we can use other functions, other differential function also, but sigmoid is one of the most popular functions. So now, as a part of this network, we have learned that how we calculate the errors at the output layers, how we update the weights while propagating the errors, back propagating the errors, and how we calculate the error at the hidden layer also. So here A was the layer neuron at the hidden layer, right? So let us now take a full example, full network. Again, we would be using first in terms of the definitions only, then we would be going for a working example. So suppose the network is like this, where we have two neurons in the input layer and we have three neurons in what? In the hidden layer, and we have two output neurons, and the corresponding weights have been marked accordingly, right? So the first task would be to give the inputs through this layer, right? Then we would be doing what? We would be using the initial weights, which would have taken. So there would be two set of weights we would be using. One set of weights is between what? This input layer to hidden layer, right? So we would have used the initialization of weights, these weights. Then similarly, there would be another set of weights between the hidden and the output layer. So there would be these weights, right? And once we would have applied, so the first in the forward phase, we would have done what? We would have calculated the activation inputs for A, B, C. Then we would have calculated the outputs from by applying the activation function, which is a sigmoid function for A, B, C. So we would have calculated the outputs for A, B, C. And similarly, then we would have used these outputs as inputs for calculation of what? The output at alpha and beta, that is the output layer. In the same method, we would have calculated the output, first the activation input for alpha and beta, and then by applying the activation function, we would have calculated the output at alpha and beta. So this is the forward phase where we would have calculated the output at alpha and beta, right? So after doing that, the back propagation of error would start, right? So considering this as the example, so let us formulate what would be the formulas. So the first thing that I have to do is, we have to calculate the error at not considering the forward phase, assuming that we know the forward phase. So I have to calculate the error at alpha and have to calculate the error at beta. So for calculation of the error at alpha, right? So the formula would go on same, like output at alpha, 1 minus of output at alpha, then target alpha minus of output alpha, right? That is very clear. That is, in order to get the error of alpha, we have to first multiply the terms output at alpha, 1 minus of output. This multiplied term would be always there. Similarly, for beta, there would be output at beta multiplied by 1 minus of output at beta. And then the term, what was the actual output we have calculated, and what is the target for it. So target is something which is labeled, because this is a supervised version. So we must have the target values for alpha and beta as a part of the supervised learning algorithm. And alpha and beta, we would have calculated what some output while giving the input during the forward phase. So there would be some kind of difference between the output and the target values that we have done for alpha and beta, right? So this is how similarly we would have calculated the errors for this beta output neuron, right? So I hope this is very clear. Now, similarly, as we have discussed, we have to do what? We have to update the weights for each and every. So that is, we have to update this weight, we have to update this weight, we have to update all these weights. So let us, for example, see how we are going to update the weight with WA alpha. So in order to update the weight WA alpha, what I need is WA alpha plus, that is new weight, would be equal to WA alpha, that is the old weight, plus what is the error at alpha, what is the error at alpha, and what is the output at A, right? What is the, and this term is basically learning factor, right? This is a learning factor which we can take any value between 0 and 1. So we'll discuss about this afterwards. So what is the error at alpha, right? What is the error at alpha, and what is the output at A? So what is the error at alpha in order to update this? What is the error at alpha that we have just calculated in the first phase? And what is the output at A, which we had already calculated during the forward phase? So in order to update WA alpha, it becomes what? WA alpha old value plus error at alpha and output at A. All these terms are known, already known by this time. So, and similarly, we can define by the same symmetry and by the same method, we can define the same formula for each and every weights between hidden and the output neuron, right? So there would be all what? There would be 6 such weights. Now, once assuming that we have updated these weights, now the next task is what? Is to calculate the error at A, B, C. These are hidden layers. So we have to calculate the errors at A, we have to calculate the error at B, and calculate the error at C. Now, in order to calculate the error at A, which is linked with both alpha and beta by the same method that we discussed earlier, now what we have to do is we have to use the formula like this. In order to calculate the error at A, we have to find again the same term, that is output at A, 1 minus of output of A. Then what was the error at alpha, that is the output neuron, into the updated weight. Have not by mistake we have not used this plus sign over here. So these weights are not old weights, these are the updated weights, right? So what is the error at alpha, and what is the updated weight between A and alpha, and similarly what is the error at beta, and what is the updated weight between what? WAB. So very simple. In order to get this error at A, what I have to do is first I have to multiply the term output at A multiplied by 1 minus of output at A. This term is fixed. And then what we have to do is, what is the error at alpha, that we already know, in multiplied by this updated weight, right? And plus similarly, what is the error at beta, and multiplied by this updated weight. So that is what is the formula. And likewise, we can define for beta, B and C also, right? I hope that is very clear. So by this time, what we have done is we have calculated, we are in the back propagation phase, where we have calculated the errors, then we have back propagated the errors and updated the weights. The back propagation of error means that we are updating the weights while going towards backward direction. Now we have calculated the output at A, B, C. Now the next job is to do what? We have to update this weights in the same manner that we did for these weights, right? So in order to update this weight, we would be doing the same thing that we did for these weights, right? So I hope that is very clear. And this is how we would be updating these weights. So all these weights would have been updated, right? So this would be the end of what? Your backward phase. So then by updating all these weights, what we have gained is like, again, we would be putting all this, the same input would again be put through the input neurons. Now, since the weights have been updated, so we expect that there would be change in what? The output at alpha and beta. There would be new values of output at alpha and beta. So again, we would be comparing this alpha and beta, that is output at alpha and beta, with its target values. There would be target value for alpha and beta. And then again, the error would be calculated. If there's no error in that case, or the error has come up to a defined range of accepted errors, then we would end the process. Otherwise, we would keep on doing this feed forward and backward direction updation of errors till a moment then there is a difference between your the calculated output and the actual output, that is the target value, minimizes or comes under a defined range or becomes null. It would never be zero, right? So mathematically it would never be zero. That is not how we actually work. We always define the percentage of error. That is how we work, right? So I hope this architecture is very clear, that how we are doing this feed forward and back propagation of errors. And similarly, you have defined for the weights, new updated weights between the hidden and the input layers. So I have told about the learning rate. This learning rate ideally must be lesser than 0.5 to begin with, and with the time these learning rates are also decreased. But as of now, you can understand that there would be a fixed learning rate associated with the network, right? So let us do a very simple example also in order to understand how the things go around. So we have taken the weights. So we have the inputs. We would start with the input A and B with the value 0.35 and 0.9. And these are given associated weights between the input and hidden, and again between the hidden and the output. So let us assume that what is the target value. So target value we have assumed. This is all just random. This is just to explain you how the things work. So target value is 0.5, right? And for simplicity, we would not use a learning rate, or we would assume it to be 1, right? So the first thing is we have to calculate the output, right? So in order to calculate the output, again by using the same set of formula that we learned, we would be doing what? We would be first doing the forward phase. So the forward phase would be what? I hope everyone understands about how we calculate the forward phase. Um, Forward phase means what? I would be calculating the net input for this neuron and this neuron, right? Suppose H1 and H2, and suppose this is the output neuron, say suppose Y. So the first thing that we would have been done is what? We have to calculate net input of this neuron, which would be what? Input, that is 0.35 multiplied by what? 0.1 plus 0.9 into 0.8. This would be net input for this neuron. And similarly for this would be what? 0.35 multiplied by 0.4 and plus 0.9 multiplied by 0.6. This would be net input for these neurons. And once these neurons, we have calculated the net input, we would be applying what? The net activation function, which is sigmoid function. And as we all know, the sigmoid function does what? It brings down the value, whatever it takes as input, it brings down the value between 0 and 1, right? So assuming that you all are well versed with these sigmoid function, because you must have learned about them in the previous classes, right? So what we have done is we by doing this we have calculated what the output neuron value after doing the forward phase in the same manner, and at last output at alpha we have directly calculated what the output at the output neurons, that one output is 0.68 and the output which is coming out is suppose 0.69, right? So we have calculated the final output. The final output is 0.69, right? the final output for the final the final output for this neuron comes out to be what? 0.69. Because once we calculate the activation inputs and activation output from this, then we would be multiplying the value of output of this multiplied by this plus output of this multiplied with this in order to get the net activation input of this neuron. Then again we would have applied the activation function, and then we would have obtained what? Something, a value which is over here. We are calculating it what? Suppose 0.69, right? I've given the values also how it is been calculated. Now the first thing is we have to calculate the error at the output neuron. So by applying the same formula that we discussed, that is the target was what? 0.5, and we have just calculated the output of the neuron is 0.69, and then again this difference between these two terms, the target minus of the output that we have calculated. So the error at this point of time is suppose minus of 0.04, right? Now we have to use this error in order to backpropagate what? All the weights. So the first we have to update the weights W1 and W2, right? That is, I'm talking W1, I've made this W1 and I've called this W2. So the first we need to update these weights. So the 0.3 would be updated with a new value, 0.9 would be updated with a new value, right? So by doing this, 0.3 is an old value. Then by applying what is the error that we obtained multiplied by input. Input was what? What was the output of the hidden neuron? The output of hidden neuron was 0.68. It has been shown above, right? So this is how I would have got new value of this weight, which was previously 0.3. Similarly, W2 would be the new weight, which now comes out to be 0.8. You can see that there's a little difference. There's been these values have decreased, right? Now, once these weights would be updated, the next thing would be to calculate the errors of the hidden layer. So suppose hidden layer have say del 1 and del 2. So in order to calculate the hidden layer by the same method that I've explained in the formulas, it comes out to be what? By applying this difference, it comes out to 2.4 into 10 to the power minus of 3. Similarly, the errors at the hidden layer 2 comes out to be this value, right? So again, once we calculate the errors at the hidden layers, then we would be using those errors in order to calculate the weights, to update the weights between the input and the hidden layer, where we had 4 weights, right? We have named suppose W3, W4, W5, W6. So again, by using the same method by symmetry that we have explained in the formulas, once we would calculate them, it would come out to be this. So what has happened is, the old error was suppose 0.19, and the new error comes out to be point minus of 18. So you can see there's little difference between this. So this error has in fact reduced. So this is how actually if the network is correct, and if the weights taken, random weights have been taken are correct and useful, then you would see that errors are decreasing in the, ideally are decreasing, although this is not necessary, but this is how the network would work. So this phase would continue till, as I've said, the difference between the target and the actual calculated output is comes under the defined range of acceptable error. So this is all about the working example of backpropagation errors. In the next case, we would be focusing more on the chain rule, that how we are using the chain rule, because as of now we have just used the formula. We have not explained that how this formula came about and how this chain rule and how the chain rule is being used and how it is assumed, right? And what all important components are there. And we would be talking about the gradient function, in fact, right? So for this lecture, thank you.